Hello everyone. Today I welcome you to the day 17 of the training in FPGA development. I'm very glad that you made this far, and sorry for the break in the last week because due to some cyclone emergencies in few of the states in India, I would like to have some break and give some time to the candidates who are actually struggling. So that's the reason I have given a break. But from today, there will be a series of learnings and I'll try to finish it before the date of the delivery, and so that I can answer all your questions with respect to the interview preparations. So in the series ending, I would like to introduce the interview preparations as well, how to build a resume and also correct type of portfolio with the projects, appropriate projects. So with that being said, let us go to the today's agenda. Today we will be discussing on sequential logic circuits example, and in the last class we have discussed on combinational logic circuits using behavioral modeling. Why do I say behavioral modeling every time? Because it is the most used and major part of the Verilog HDL structure that you write and that you see in the development in the IDE environment. It will be based on the behavioral modeling. So that is the reason, and as I said, 95% of the codes will be based on behavioral modeling, and it is easy to tackle with that in that scenario. And the second thing, after behavioral modeling, we will be going to the switch level modeling with examples. So let us see what type of example circuits we are going to, and these are the most essential sequential logic circuits that you should be going through in behavioral modeling, and keep a reminder of these things and recollect them and review them once in a week or once in a month, so that you will be getting used to these modeling examples, and so that when you are developing the real-time project, these elements, these components are most useful while developing. So yeah, let's dive into the today's session. Let us discuss more about the sequential logic circuits. What are the sequential logic circuits that we have today? And as I already do, yeah, I would like to introduce about some of the sequential logic circuits which are majorly important in hardware development in the FPGA or in the digital system design. When I say digital system design, it's more about sequential and combinational logic circuits. If you don't know the basic difference between combinational and sequential logic circuits, the major difference is clock. Combinational logic circuits doesn't have any clock, but sequential logic circuits do have a clock, and they work and they will be enabled only based on the edge triggered or level triggered clock pulses. So we will see that in the next coming slides, but let us start from the most essential examples of sequential logic circuits. So sequential logic circuits. So first thing is D flip-flop and counter, pulse generator, where some of the digital system design circuits require pulse generation for enabling clock or some signal generation or for the clock pulses, anything. So it's a common pulse generator. We have different modulus for it, magnitude of the pulses, like module 3, module 11. It's like division of the clock. Clock will be divided based on the number of pulses in the given time period. And major circuit, ring counter and the Johnson counter. There are different types of counters, but again, in addition to this counter, one should know about ring counter and Johnson counter. The next thing is shift registers. These are the most essential things when you are dealing with some kind of registers in terms of data, to push forward, to shift right, to shift left, to shift downwards. So it's like the data transition from one position of the memory to another position of the memory, or one position of the circuit to another position. Let us take between input and output. So we need shift registers to push our data. So we have four different types of shift registers, and there are other types of shift registers as well. One is SISO, serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. I will be discussing these things in detail with the circuit diagrams to make you understand, and also the Verilog code beside it. So next thing is linear feedback shift register. You might have heard of this linear feedback shift register because to have a random number generation and some counter generation, so it gives you some pulses. So the actual linear feedback shift register is mostly used for random number generation and some other computational applications. And in the next level of all these are behavioral modeling, and coming to this next two are the switch level modeling. So these two belong to switch level modeling. One is CMOS inverter and CMOS NOR gate. Switch level modeling is nothing but when we have a FPGA architecture, you might have seen a CLB block, and beside two CLB blocks or between two, one there is one switch level modeling, and in the edge or in the outer boundaries of an FPGA architecture, we can see switch level modelings with IO buffers and inverters. So in that IO buffers, one of the circuits is CMOS inverter circuit and another one is CMOS NOR gate, and these are the most essential and most important to know. If you know these things as a basic essentials, you will be way more familiar than anyone else while developing the hardware architecture on the FPGA using IDEs. And now in this training, we actually want to learn the Verilog HDL, but in the industrial large scale applications or in the real time projects, you will be taking the help of IDE tools like Xilinx, Vivado, EDA tools, development environments to generate the Verilog HDL. In the beginning of our course, in the day 7 or 8, we have generated a microblaze processor, and what we have done, we have used IP integrator to generate the Verilog HDL. In the same way, for this CMOS inverter or NOR gate or for any larger circuit involving all these elements in a group, then the whole bunch of modules or blocks are written in the Verilog HDL in a large file, and that file can be generated with the help of EDA tools. So that being said, let us go into the each element. First one is D flip-flop. In the D flip-flop, what is D flip-flop? D flip-flop is a sequential logic circuit, everyone knows, but it works on the edge triggered device. Like edge triggering is nothing but when you have a clock pulse given to the D flip-flop. For example, if you have a D flip-flop here and you have given clock here, for that, if you have given pausage of the, if this is the time period, given this is the time period, let us say 10 nanoseconds. Why I am repeating all these things again? So to make you understand. So between this time period and for the next clock cycle, again the input will be taken from this edge, pause edge. This is the positive edge, and if you consider negative edge, like some of the sequential logic circuits or in the some designs, everything will be triggered on the negative edge of the clock. So it will be triggered on the negative edge of the clock. So either the positive edge or the negative edge, we write in the always block. That means we are enabling the flip-flop to function. We are enabling flip-flop to function or work. So to make this flip-flop switch on, we need to give a pause edge or the neg edge of the clock such that whenever the clock pulse has a positive rise, positive edge, then the D flip-flop is switched on, or else it is stable or it is ideal position, it is at ground zero, so there will be no operations. In the same way, a D flip-flop, we now know that it is edge trigger device. So when we are working with D flip-flop, we need to write an always block saying that always at the rate pause edge of the clock. We will see in a bit later. And then D flip-flop takes the input at D port that follows either positive edge or negative edge of the clock. That's what I have said right now. And this is followed through Q and generates Q input. So whatever the input is given at D flip-flop, that is given at the pause edge of the clock, and whatever let us say a bit of 1 is input to the D port. So that D port bit or data will be transferred to the Q. This meaning is nothing but this is followed through the Q and generates Q input. Q input is followed by the D flip-flop for each clock pulse, whether it might be pause edge or neg edge. This cycle of data flow is followed till the next clock cycle of pause edge or neg edge. For example, if you have a clock pulse of 10 nanoseconds, let us say, take it from here and till here, it is 10 nanosecond. Okay, and you have a data of one bit, only one bit. So what is the D input? It is 1. So it is D, it is clock. And what will be the Q according to it? Q will also be this one if it is positive edge. So I will try to explain this in bit pictorial way, but I'm giving a vague explanation here. So things apart, that is about D flip-flop. The Q input will be followed through D port for every positive edge or negative edge of the clock. That is the meaning of D flip-flop. Hence the data flows between D and Q in this way. So this cycle of data flow is followed till the next clock cycle. I mean, for next clock cycle, at this point, another data. If it is 0, if D is equal to 0 and here D is equal to 1, Q will also be 1 and Q will also be 0. If D doesn't change, Q will remain until the D value changes. Okay, so that is it. And coming to the next, what is the Verilog modeling, behavioral modeling of D flip-flop? Let us understand. This is the D flip-flop figure. This is how the block represented D flip-flop, and let us say it is a positive edge triggered and time period will be taken in terms of nanosecond. You should be remembering all these things. What are the units of time period? And this is a edge triggered clock cycle, edge. And what is level triggered? Level triggered is nothing but the entire data response on the level. So this is level and this is edge. Simple difference. I think some of you are very new. That is the reason I'm being a bit slow, but try to catch up with this. And module D flip, name it. This is the first step or first part. As I say, whenever you write the Verilog modeling, think about what type of parts, what are the parts that I need to develop Verilog modeling. So it will be easy in the pipe level modeling as well, pipeline implementation in the development of the processor or development of the architecture in the FPGA. So there is one type of implementation called pipeline implementation. I'll try to give an example of that, but it's a very complicated topic as of now. But understand behavioral modeling in this terminology, where this D flip-flop works on the edge triggered, and we need to make it functional and make it enable on the architecture such that we are writing first part of the Verilog HDL as the declaration. So what is the mistake? You need to semicolon, end the module declaration with a semicolon. So that is the syntax error. So that's the reason I want to show some of the syntax errors you people are doing while developing the videos. So whenever you understand something to develop, there is a blueprint for that part or for that line of Verilog HDL code. So for example, blueprint here is you need to start with module, name it, name your device. Module is nothing but device, element, circuit, or whatever you call it as, the entire design. So that design will be called as module. Here my design is D flip-flop. So for that module, name, and what are all the inputs and what is the output within the brackets. Done. And you need to end up with semicolon. Hence, now I will change this. So yeah, that is one difference. Now coming to the first part is done, hence it is done. Second part, input D, clock, reset, output Q, register Q. What are all the outputs available? Those are registers. And what are all the inputs available? Those are wires. We don't want to mention they are wires because those are single bit inputs. Hence we didn't declare any size of them. It is a single bit. So 1 bit at a time, clock and reset are 1 pulse or 1 bit at a time. Output is also single output because it follows the D. What about Q bar? Why didn't we declare it as another output? It's nothing but if you have one output and if you negate it, Q bar is nothing but not Q, right? If Q is equal to 1, what is Q bar? It is 0. So hence if Q is equal to 0, Q bar is equal to Q is equal to 1, Q bar is equal to 0. How are we getting Q bar? It's not a separate circuit, but we have mentioned a separate port to derive the output internally from the available output Q. So Q bar doesn't require any special declaration. If you are changing it to some other variable, in some other black box, let us say some random box, if you have two different outputs like y1 and y2 which are not internally related, you need to declare as y1 and y2. Don't get confused in this, guys. It is quite simple. Understand in a flow. So now this is the second part done. Second part is nothing but input output declaration. I don't want to repeat this for every Verilog code that we are going to write, but you need to figure it out. What is the first part and what is the second part? Okay, then coming to the third part, we need to start the block. So to start the block, to enable the block, what are we giving? We are giving it positive edge of the clock or negative edge of the reset. So here we can also give another circuit. I mean, we need to reset the block, right? Whenever the data is stuck or whenever the data is in delay, or if we want to erase whatever the static data ones or zeros we have, that to be erased temporarily. So for that we use reset pin as well. So clock pin, clock reference will be taken, and reset pin also will be taken. So and also reset, why do we need reset? Sometimes for the ease of simulation. So whenever we are simulating, right, we are testing giving 1 and 0 and also again 1, some random values we are giving. So it will be like 1 0, for example if we give 0 and 1, and it will be 0 and again 1. So if this is the data 1 0 0, if this is the data that we are trying to give in the reset, and what if we want to give 1 0 0 0 like this? So if you want to give this kind of data for the D input in the second round of simulation, what will you do? You can't overwrite the data on the same before port. You can't write. Hence we need to reset the data, reset the clock that is going to the D input, and when you reset the entire circuit, again D can take another input. So one thing at a time. That's what reset is used for in the simulation as well. So hence we are declaring positive edge of the clock or negative edge of the reset. It should act on either of these, right? Positive edge of the clock or negative edge of the reset. When reset is low, it works, or when clock is high, it works. And another thing is, low means negative negative edge of the reset. So begin very simple if else circuit. If reset is enabled, then this means reset is equal to 1. The circuit is clean. No input at data port D or no output at Q. Empty. D flip flop is empty. Then you need to write Q is equal to 1 bit B0. So what we are giving here, we are assigning a value. Assignment operator. We are assigning a value of 0, 1 bit 0 to the Q. I'll mention it with another color. So we are assigning a value of 0 to the Q. Now if reset is equal to 1. If reset is equal to 1, what happens? Then Q is equal to 0, because initial D is having no value. 0 or 1, no value. If there is no value, Q should be at position 0. We don't know whether it will be 0 again or 1 again. Else if reset is not equal to 1, else means opposite condition of the if. Else reset is not equal to 0. Then if reset is equal to 1 now, here reset is equal to 1. Then at the negative edge, fall edge, here Q is equal to 0. And if else reset is not equal to 0, Q is given with the data of D. What is the value of Q? What is the value of Q again? D. Whatever the value at D, that will be followed through the Q. Hence, else condition works like this. So whenever D flip-flop wants to have some data gone through the output Q, then reset should not equal to be 1. That reset is equal to 0. Got it? AND 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 module. This is how you can write the D flip-flop. In the same way, we are going to introduce ourselves to the part side modeling. 1, I'm just declaring again, 2, 3, 4, and this is again 1. But I'll mention it as 5th step, because if you don't end the module, your module is not enabled, or your module design will have a big syntax error. So hence, remember, in this part-wise model, same type of part-wise model will be given, will be discussed in the same other sequential elements. And D-latch, a shorter example. D-latch has this clock which is at level triggered model, and this is not the edge triggered clock cycle. This is a level triggered. Level triggered will be shown in this way. And module D-latch, you have D, clock, reset, and Q. Q is the output. All these are inputs. Input and output declared. Part 1 and part 2. Begin and end. This is the step 3, and this is the step 4 and step 5. This is related to the part 1. You can see if reset Q is equal to 0, and if clock is equal to, else if clock is equal to 1 at the level triggered. So that's the reason we didn't mention anything as pause edge or the neg edge. Edge is nothing but edge triggered, but here we are writing clock and reset at the right when clock is equal to 1 or reset is equal to 1, or any change in the clock or reset, then always block will be functioning. So what do we call this as? This is called as always block. Always block. Remember, this is the major step for the functioning of the D flip-flop or D latch per se. Now we have synchronous and asynchronous D flip-flop. What does this mean? This means something like only synchronous reset is nothing but only at the rate of passage of the clock, but at the asynchronous reset we can also consider the negage of the reset, either this or this. At any point of this changes happen, for example, as I said, for the passage of the clock and for the negage of the reset. So this is reset and this is clock. For these changes, any one of these changes, it is not synchronized, it is asynchronous. For this, any one of these change, the values will be considered in this scenario. Q will be 0, and else if reset is equal to 0, then Q will follow D at this point of the reset. When reset is equal to 0, it is 1, it is 0, 1, and it will be again 0. So hence that is the major difference between synchronous and asynchronous D flip-flop. Remember this as a important note. You will be getting this application in the real-time project. Based on that, you will again remind yourself about this example in the synchronous and asynchronous. Sometimes we require asynchronous reset or asynchronous D flip-flop application based on the design complexity. Coming to the next thing. Now let us move on to the another example of sequential circuit called 3-bit counter. Counter, we already know the example of counter. What it does in the beginning of our classes, I have introduced counter as it increments the counter. I mean, for example, there is an initial value of I at 0. What does the counter do? Counter will be incremented for each bit of a value. Hence it will be counted in a sequence, whatever the highest bit that you want to say. But what about the 3-bit here? 3-bit says counter will be having a 3-bit of the size. So your values of decimal 0 will be written in terms of binary 3-bit. Hence, in the binary value of 3-bit, what is the maximum decimal value that you will be getting? That is nothing but 2 power 3. Hence, your total values of the counting value can be 8. So, in this reason, we can say 0, 0, 0 and 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1. How many values do we get? 1, 2, 3, 4, 5, 6, 7, 8. So these are the 8 values or 8 counting numbers that counter can do with a 3-bit. If your counter is a 4-bit counter, how many values you will be getting to count? It's most basic question, but I can say it is 2 power 4. So you need to have 16 values. So whenever I say 16 values or 8 values, start from 0. So where do you need to start? You need to start from 0. And if it is 4-bit, consider 4 bits of binary zeros and start a sequence from 0, 0, 0, 1 to 0, 0, 1, 0. I don't want to write all these things. You write and figure it out. Already we have done many times. 0, 1. I'm writing decimal values here. And if my decimal or hexadecimal, let us say, and if my hexadecimal value is f or 15, then my binary 4 bits counter can give me the output of 4 ones. This is the ending point and this is the starting point. That is how a counter works with an increment of each bit. So what are we doing? We are adding +1 for each value. So after adding +1, we are getting, so 0 plus 1 1, 1 plus 1 2, 2 plus 1 it is 3. Why am I giving such a basic beginner level explanation to all these things? Because I want to use these counters or sequential elements or all these logic circuits in a series, in an application oriented, when I teach you a project or when I make you do a project. So that is the major reason I want you to understand these counters, how they work. So coming to the uh, modeling, coming to the writing of Verilog HDL, you can see part 1 is about declaring timescale, that for every Verilog HDL code, it is good if you write a timescale unit, like if you mention this system task, because whenever we use somewhere in the test bench simulation, if we are using #10 or #500, it says after 500 nanoseconds of the clock you do some task or you assign some value. So in this way, for doing some operation, you have to give some hold or delay, time delay, to make a simulation happen. For those mentioning of the nanoseconds, you don't need to mention ns. Hashtag 500 will be taken as 500 nanoseconds because of this timescale unit declaration. And coming to the part 2, declare the module name and IO ports. Yes, we are declaring name, module name, counter, input and output, reset and output is Q, and inputs are clock and output is Q. It is a 3-bit counter, so the output can be 4, because if there is one another value that you want to add, if that is an empty bit, there will be no issue. But if this is 2, 0, that is exact application of the 3-bit counter, and if it is 1 bit 0, no, you shouldn't be writing in that way. You can mention 2 colon 0 or 3 colon 0. So anything works fine. There is no hard and fast rule for mentioning only simple one specific definition. If you write excess, there is no harm in it. And then when we write declaration for input wires, output registers, we need to declare what are the wires and registers. All inputs are wires, all outputs are registers, we have declared. And for beginning of the process, in the part 4, we need to begin the process, logic, function, operations, whatever we want to do with the counter or do with the module that you have mentioned. That functionality will be given in terms of this always block. So always block does the maximum functionality of whatever inputs and outputs of the process you do. So this always block will be your black box of magic, where the actual operations happen. And if reset is equal to 1, if reset means reset is equal to 1, if reset is equal to 1, reset is equal to 1, then Q is equal to 0. If reset is equal to 1 means when the clock is like this, if reset is equal to like this, reset is 1, this is reset. At this particular time of clock pulse, Q will be 0. Else if reset is not equal to 1, then Q will be incremented. That is how this loop works, and that is the basic design development of the 3-bit counter. And in the same way, we can generate pulse generator. If you can see, this is the pulse, I mean clock pulse. And why do we take pulse as the output? Because we need to mention for every 3 clock pulses. So mod 3 is nothing but for every 3 clock pulses there will be a pulse. So 1, 2 and 3. So there are 3 clock pulses, hence after 2 clock pulses, third clock pulse will be there will be an output. For example 0, 1 and 2, there will be a pulse, and again 0, 1 and 2, third mod 3 at third one you have a pulse. So now entire clock period can be divided by 3. That's how the pulse generation works. So now what are we considering now? We are considering the new pulse. That is the application of pulse generation. So we consider new pulse. So but in the larger pulse we might have clock, 3 clocks, 3 clock pulses. That is the major reason. But let me put it in another way. If we take 3 clock pulses and we want to consider for every 3 clock pulses we want one single operation to be done, like a plus b. So for every 3 clock pulses a plus b will be done. Simple. But what is our new clock pulse here? So if this is the clock, we are considering a bigger pulse above all these 3 clock pulses. So now again for every 3 clock pulses we are considering another pulse, high, or this is normal pulse low. So this is 0, 1 and 1. Hence it will be look like new clock pulse, new clock reference. Let me take blue. So this will be new clock pulse. So for that reason we are considering pulse generator. So what are the major inputs and outputs? You can see from the Verilog module, part 1 module pulse gen 3. You can mention whatever name you want, but inputs are clock you have, reset will be there, Q and Q next will be there for our reference, and for the output Q next is the next state and pulse will be the output. And in the input clock and reset, output will be Q and Q next as we have mentioned, and pulse will be output this. And why are we taking Q and Q next? Because to have some reference for the clock pulse of the data. For this pulse we are actually working it. So then all outputs are registers as I said, and all inputs are wires. Okay, so again assign the value of Q next as, if Q is equal to 2, that means when the value of Q is 2 is true. If it is true, take the value of Q next as 0, Q next will be 0, and or else if Q is equal to 2, if it is false, that means Q is not 2, Q is 1 or 0, then Q will be incremented at false. That means if Q is equal to 0 or 1, then Q next is equal to incremented Q plus plus. Or else if Q is equal to 2, then Q next is equal to 0. So hence 0. What happens? The pulse is equal to value 1, or else pulse is equal to 0. These are the assigned values that we want to give. But how will we know whether the Q value 2 or 0? That will be known by the counter. Always at the rate passage of the clock. If reset is equal to 1, Q will be 0, else Q will be the Q next. There ends the module, end module. So hence pulse generation will be done based on the present value and the next value we are taking in that sense, and the reset should be low. When the reset is equal to 0, that means this reset is equal to 0 is nothing but here. Reset is equal to 0. What is happening? Q is nothing but Q next. Q is following Q next. What is Q next? Q next is nothing but increment of Q for every 3 values: 0, 1, 2, 0, 1, 2. This is the loop. It goes. Okay. Coming to the next, module 11 pulse generator. This will be the same as module 3, but for every 11 pulses, if you can count, I'll take it here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at the 11th pulse, 11th output or 11th clock pulse, 11th Q output, you can see a pulse. In the same way, from here, if you can count, another 10 and 11th will be the pulse. Here, 3rd will be the pulse. 11th will be the pulse. You can see there will be no such difference between codes. We assign input output as it is as the same, but only difference is if Q is equal to 0 and whatever we write in the code for here in the pulse generator output as 1 byte comma 0, it is a Q is a 2-bit, and in the same way we are writing Q is equal to 11, we can write. Then Q next will be followed according to the 0, or Q next will be Q plus 1. Simple. The same hierarchy will be followed. As you can see, this is how the pulse generation happens, but for every 11 pulses. Okay. Then what is our next step? We are just considering all these bits. I have just enlarged this bit. If you can see, this 200th nanosecond of the time or picosecond, whatever might be the clock. This you can see for every clock pulses 0, 1, 2, and for every 11 clock pulses or some bits of data for 10 pulses. 11th pulse will be your reference clock pulse, new clock pulse. For example, if you have 10 clock pulses like this, so on, and for the 11th clock pulse you will have the pulse, new pulse as, and now at this point your output will be following at input. Okay, so that is how you can work with counters and pulse generators. Coming to the shift registers, we have shift registers for temporary storage of data. In the stack of memory, we have group of registers that can store bits of data or bytes of data. When I say byte, 1 byte is equal to 8 bits. Remember this, guys. This might be your interview question again. Don't get confused. 1 byte can be 8 bits. And if I say 1 byte register, you have 8 bits register. For example, you have 2 byte count, 2 byte memory. That means this memory register can have 16 bits of data. Okay, remember this, don't get confused all the time. 2 byte memory is nothing but 16 bits of data. That means 16 bit of data can be looking like F, and B. Hexadecimal. In hexadecimal representation, F is 4-bit binary, 4-bit binary, 4-bit binary, 4-bit binary. B can be like 1, 0, 1, 1. F can be 1, 1, 1. This can be 1, 1, 1, 1. And this is 1, 1, 1. So what are we having here? 12 ones. 12 ones and 1, 0, 1, 1. This can be B, and this all can be F, and F. This is how it is represented. Got it, guys? We have shift registers for temporary storage of data. Simple application. I have explained how data will be in the memories, and these shift registers are also used for data transfer and data manipulation. Sometimes we are left shifting, right shifting for play with the memory data, and manipulation is nothing but working on the data flow, that how we want to design the data flow, whether it might be top down or bottom up, however we want this shift register to be worked. And we have different types of shift register. As I said, serial in, serial out, one type of shift register, parallel in, parallel out, and also serial in, parallel out, and parallel in, serial out. There are 4 types of shift registers used to produce the time delay. Basically, when you have 2 types of memory or 2 memory blocks, one memory is pushing data to ALU, let us say, and second one wants to push the data to ALU, but first things first, it requires some 5 nanoseconds of time to push the data to ALU. Then it should wait for next 5 nanoseconds. So it should wait for next 5 nanoseconds, then it can work for from the 6th nanosecond. Okay, what time it will take for this memory? It will take another 5 nanoseconds, let us assume. So from 6th to 10th nanosecond. Got it, guys? Hence, this type of time delay to wait for 5 nanoseconds for this, if we make some combinational circuits at the output or at the input, then it will be having some delay on its own, so that it will work synchronizedly in a particular parallel amount of time. So 0 to 5 block A of memory will work, and 6 to 10 nanosecond block B of the memory will be working. So, but block B should wait for first 5 nanoseconds. That's what time delay is nothing but. Time delay can be in terms of many definitions, but one simple example can be in this way. So let us see how these are constructed. So a quick summary of Verilog modeling will be designed in this way. It's a basic implementation of how the design works and how is the data traveled between input and output. All the shift registers are based on one simple scenario: input and output, data transmission between input and output, how the data comes and how data leaves from the register. Register is nothing but some kind of memory or some kind of element or the device which can store bytes of data or bits of data. Simple, make it short. So serial in and serial out, it's a first type of shift register. If you want a basic delay of the data going in a sequence, that is the data will be first bit, let us say 1011 is your data. So this LSB, if it is LSB, and if you take the leftmost thing as MSB, and this bit will be transferred first and 1, and after 1 goes here, another 1 will come. Let me change the color. In a sequence I will be explaining. Forget about the Verilog, we will discuss it in a bit. So next one will be going through the one here, and then that one will be sent through one, but here the existing one is there, right? That will go here. So each data will be pushed in this sequence. So if there is 0 and 1 and 0 1, it goes in this sequence. Hence for every each bit, if this is the data, I have given another example, but here we can see 0 and 1, 0 and 1 is the data. So how it is going? 1 will be coming here and it will go in a sequence. Then 0 will be followed, this 0 will be followed, and 1 will be followed, and 0 will be followed. So serial input, it's in a sequence. Hence the delay is counted in this way. But for that, let us say module name, clock, input and output. For each clock, data is push forward to the data through the D port in the D flip-flop, and output register SO, and temporary register will be there because there is one thing in the Verilog HDL. In the always block, you cannot write an in-out in-out register. So for example, in-out wire, for example, in-out can be how we can say it is a bidirectional. So if you have declared a bidirectional thing in the register language, and that kind of wire or register of bidirectional representation cannot be used in the always block for the assignment of values. Hence whatever the value that you get in the temporary outputs at each flip-flop, that can be stored here and that can be pushed to SO. So temp variable register temp, and for that temporary register you can store the data here for the first 3 bits and the input 4 bits, and that 4 bits will be stored in temp3, and that temporary variable data will be assigned to SO. Hence the output is collected in this way. It is a sequence, it goes in this way, or how we can say this way, this way. So it is taking some time. So that's what the time delay is counted for. Next we have serial in parallel out, and module serial in and parallel out is nothing but same ways how the data is getting through the flip-flops and how the output is output data is collected from the flip-flops in this way. So we have given the inputs in a sequence, right? All these inputs are traveled here and outputs are collected at each point with a shorter delay than the previous one. What are we doing here in the previous one? Whatever the output you get, that output will be collected at the serial output. So only the data flows here, right? First 1 will be coming, next 0 will be coming, and then 1 will be coming and 0 will be coming. So that is how data is collected here in a sequence. But how the data at serial in parallel out is getting out, data is sent in a serial input for every input of the flip-flop, we have a data like 1 0 1 0, and the output is collected at parallel. So 1 0 1 0. So data is collected in this way parallelly. Instantaneously it will be getting at parallel output for every flip-flop. So why do we use flip-flops in the design of registers? So group of logic circuits are called as flip-flops. I am just explaining the hierarchy. Group of logic circuits like AND, NAND, or XOR or logic gates combinedly called as a flip-flop or a latch. And from those flip-flops, if you combine them, that combines a storage of data, or that combines a temporary storage of data. That storage of data, or that holding of bits of data, is nothing but the same functionality as the register does. Register can be a memory, or register can be a block which holds the data for a temporary amount of time or time period. So serial in, serial out, and serial in parallel out is done in the same way. Like we have a temporary register, we have a parallel output, and for every passage of the clock we can have temporary variable getting the data at outputs for every temporary 3-bit and input, serial input. So at that point, PO can be taken as data collecting from the temporary variable. Earlier it is SO, now we have mentioned as parallel output. So that data will be collected in a sequence. So this is a sequence of operations, sequence of statements. For example, these are the sequence of statements. And now what are we doing? We are getting the data into the temporary thing, and that data will be assigned to the parallel output simultaneously. Assigned. And now we are collecting at parallel in and serial output. Understand, this is nothing but we are giving the data at each clock pulse. For first clock pulse, all the inputs are given at given the data at inputs, and all the outputs are collected in a sequence. Through the logic circuits. Why did I drew this logic circuit? How these are connected in this? This is how the parallel input and serial output register is counted. For example, we are giving data parallelly. Consider these lines, parallel inputs we are giving for each flip-flop at D inputs. Now I am representing output with a red mark. So output is collected in a sequence, and that output is loaded in a sequence, and that output is collected at one single output. So hence with some delay from this queue, it is going to the combinational logic. Let me erase all the ink and see one serial data output, how it is going through. From this data, it is going through some combinational block. Combinational block is nothing but logic circuits, and from that data is going, and here Q follows the input of D, and the parallel input, the data D will also be getting operated from the parallel input. So parallel input will also be there, and Q will be getting an output based on the operation, and this Q will be loaded again in a sequence, and that sequence will be going through this. Understand the functionality here, and then data will be coming out in a sequence until unless, here you can see we have not collected any output data at any point of the time. That is the parallel, serial output called as. But parallel input, we are loading at each instant of the clock period parallelly at point of time. When we want, we are loading the parallel input. But what you need to remember is, you need to remember the logic combinations, how these are designed. Okay, so this shift is nothing but this time pulse, this shift buffer will push the clock pulse. For every clock pulse, it will push the data through this logic and through the wires. So this shift buffer is used in that way for to produce some clock pulse to this AND gates, okay, to OR gates. If 1 and it will be 0, and if 0 it will be 1. So values will be changing alternatively. Hence we have used shift buffer. You can see clock, parallel in, load and serial out. Input loads are nothing but clock and load are the inputs, and output will be parallel input, and output register is serial output, it is an output. And always at the rate of passage of the clock, if load, if you have some data here, or if you have data here, then whatever the value in the parallel input is transferred to the temporary variable, and from that temporary variable each bit will be given to the output. So the last bit will be sent through the serial output, and all the remaining bits will also be sent through the temporary variable. So here don't get confused again. Temp is nothing but temp array from 0 to temp 3. Okay, so this is how a variable or an array or the temporary variable can be represented from 0, 1, 2 and 3. So hence all these values will be same. There will be slight difference in the Verilog modeling, but if you understand one, you can always remember all these things. This is the Verilog code. Try to implement in the easy EDA playground on the online simulator. And hence the last but not least, parallel input, and we are giving the data as parallel inputs like this way, and we are also getting the data collected with a parallel output. This is the most fastest implementation. I think if we have 1, 1, 1 and 1, there will be no delay. Whatever the delay in the D flip-flop, that delay will be counted, and we will be getting 1, 1, 1, 1 at the same instant of the time whenever the data is loaded. Remember, if you give the data of F, and you will be getting data of F instantly. So it is very simple implementation. You can see parallel out is nothing but parallel input. What are we doing in these always blocks? In every always block of each of these registers or any other design, we are establishing a relation between input and output. How the output data is collected, how the input data is sent. I'm just repeating, this is the same. So think of this kind and understand these Verilog modules in the same way. And if you get confused, just let me clarify you again through the doubts. You can reach out to me. And yeah, these about the shift registers, and we have a special linear feedback shift register. Why do I want to explain this design? Because there is one fun task that you all can do about random number generator. Why do we need such a random number generator? Major application of the random number generator in the industry is nothing but encryption of the data. For example, you have a device of FPGA and you have designed linear feedback shift register to generate random values, and those random values will act as an encryption for the password or for any cloud server. Imagine you have a server hardware sitting remotely in some part of the US or Europe, and there you want to implement some server encryption such that data will not be hacked or data will not be intrigued. So for that kind of encryptions, you need to generate some very random values such that no human can think of or some random person can get through it. For that kind of linear feedback shift register application or random number generation, FPGAs are implemented with these LFSRs using XOR gate. But why did I give this kind of polynomial equation? This is nothing but it is a 5-degree polynomial equation where you have 5 bits of data. If you have x power 32, you have 32 bit of linear feedback shift register. See how encrypted is your data. Your data of 128 GB will be encrypted with a password of 32 bits. Can you imagine what is the password with 32 characters in it? No, you can't crack it. Hence, that is the reason we have Aadhaar cards in India for any data encryption for our own personal information of date of birth or bank details or PAN link to the Aadhaar. The Aadhaar itself is encrypted with a 16 16-bit encryption, like 16 characters of random values. It can be ASCII, it can be binary or any other thing, but imagine it is a 16 digit encryption. Now that is how we can generate a random 32-bit data. For example, if I write some random values 1 0 1 1 0 1 1 1 0 and again all ones, and I don't know whether I can write only zeros at all point of time, and I can end up with 1 1 again, and I will end up with 0 1 1. If this is the binary value of some 24 bit or 32 bit, can you imagine what is the actual value of it when you want to calculate it? No, you can't calculate. Are you taking 3-bit representation of it? Are you taking BCD, or are you taking 4-bit binary, or are you taking 8-bit binary? You would never know. That is how computers work. They have their own ASCII value that can be interpreted into binary, and that's their own language that we don't speak. Sometimes we can speak in binary as well. Things apart, that is the major application for industrial. So you have done a project and you have remotely installed your FPGA in some other remote location. There you need to encrypt the data. How will you encrypt the hardware? It's only because of linear feedback shift register or some kind of application similar to this. But how can you decrypt it? How can you decode it? It is based on the same loop of application. So hence, let us understand, we have a 5-bit polynomial. I have taken some random example, x power 5 plus x power 3 plus 1, and you have 5 bits of data, and for those 5 bits of data you can see module linear FSR I have written. You have clock as input, and you have outputs, like you will be having reset as well, because every time you generate one 32-bit or one 5-bit of encryption, you need to reset it again every time for random generation. For example, you have generated 6 number, then immediately you need to generate some 3 or some 9 or some 4 2 1, some random value. Hence, to generate the next coming random number, the previous value should be erased, should be set 0. So for that reasons you need to have reset. It's a common term, clock and reset. And why? And one more thing I want to add, when you are writing Verilog HDL or VHDL with the inputs and outputs, right, you might declare with your own names. Like I have written clock here with full name, you can write CLK, or if you are comfortable you can write CK as well, but whatever you mention here in the input, use it throughout the Verilog HDL code. You can't write CLOCK here and you can't write CLK here. It won't match. So whatever input you declare in the first part, in the second, in the inputs and wires, you need to mention them and assign the feedback value. Like y um, feedback value can be like XOR value. This is an XOR operator. We have discussed about operators, right? Remember, this is the XOR operator. Y of 1, like some y of 1 value I have taken randomly. This connection can be taken from any of the inputs or any of the outputs, and then you can mention that XOR 0. So for example, what did I take here? This is some output at the 5th bit and this is some output at 3rd bit, right? So you can take y of 3 XOR y of 5, but instead I have just mentioned 1 XOR 0, and then always at the rate posage of the clock, posage of the reset, means clock should be posage and reset should be the same. Both should be the same. Both will be same most of the times. Clock and reset will be the same clocks, just for the internal references. And for these both, posage of the reset or the clock, if reset is equal to 1, yes, if reset is equal to high or 1, high and 1 are same, then output will be starting at value 1. You all know 4-bit binary 0 0 1 is nothing but 4 is a size, B is radix, size of data, okay, size of value information, size of data, size of value, everything. This size, what is the radix? Binary. I can take H as well, hexadecimal. I can also write decimal, only decimal. So D. Likewise, I have taken 4 tick B 001. When I say 4 bits, you have to write 4 bits of binary. When I say 3 bit, you can write 001, 3 bits. When I say 2 bit, 01. When I say 1 bit, 1 bit 1, it is simple 1. 1 bit 0, it is simple 0. Understood? So don't get confused at this type of notation. It is not new. We have already used it. Else y is equal to concatenation of the data feedback. So whatever the feedback is given, this is the feedback. This is how feedback is given. When the output is gone into this thing and we have taken the feedback as the operation. See here, feedback is equal to y1 into y0. Okay, too much of clumsiness. Now here else y is equal to feedback and y whatever the value of y4 colon 1 and end the module. Hence you will be having output as some random number generated. Okay, whenever you reset, always output will be the value of 1, or else y can have a value of feedback. Got it? So yeah, concatenation is nothing but you get the value here from y. Next, switch level modeling. This is the end of circuit. This is the inverter, CMOS inverter circuit. We have PMOS and NMOS connected in a NOR. As an inverter. Inverter is nothing but NOT gate. So whatever the value, you will be getting the exact opposite value. So in the hardware description, in the switch level modeling is at the IO buffers, as I said, at the outside of the FPGA. They are surrounded, or they are in between two CLBs and one SM. Those are connected in this way. But module CMOS inverter, that is what we have named. We have output and input. We have power and ground. Those are the ports and pins. Output and input. And supply 1 and supply 0 are the declarations of power and ground values. These are the functionalities that we can have this as the input and output, how we have written. Those are predefined, but we can mention as supply 1 and 0. Supply 1 is power, like if it is high. So have a hard and fast rule. Remember it as a thumb rule. Supply 1 power you can give, supply 0 where there is no value, it is 0, it is ground. Hence PMOS is a function. PMOS is a function predefined, or the circuit that you already know. It is a predefined function that we can take, like AND or NOR. You can take it as a gate. So PMOS, that PMOS has output and inputs. NMOS, it has one output and all other inputs. Usually power and ground will be in out pins. Remember, in actual VLSI, in anywhere, the representation of the power VDD or ground GND or VSS, sometimes these power and ground ports are considered as in out. So those are bidirectional. Hence for them you need not to be mentioning in or output or input. You can take it as in out. Bidirectional. It can flow from and in, from and to. So output, power and in, out. PMOS, consider it as PMOS. You have power at one side, input at other side and output at other side. And if you consider NMOS, you have output on the other side, ground as other side and input in the other side. Hence that are declared and end module. Hence this is how CMOS inverter works. Power connected to VDD, and here this power connected to VSS, which has no value, it is 0. Hence it is ground. For our representation, we have VDD here and VSS usually. That is all. And same as with the NOR circuit, once you understand the circuit, how these are connected, and I would also suggest you to remember these circuits, NOR circuit. And for this NOR circuit, we have VDD input X, output input Y, two inputs. You can have mention as A and B as well. Two inputs and one output, and ground, whatever ground we get. Likewise, as an OR circuit, you can have also NAND circuit if anyone wants to try, and if anyone wants to implement this kind of NAND circuit, that is always welcome. You can always come and speak about this. And the representation of NOR and NAND, those are way more required. Representation of NOR and NAND are nothing but connection of PMOS and NMOS in a series with PMOS connected in OR combination and NMOS connected with an AND operation. So you can get this done here. Usual stuff: module declaration, inputs and outputs, wire is nothing but connection between two PMOSes, and that wire is Z here. Think of this small part as Z. And supply 1 power, supply 0 ground. Same declarations for the switch level modelings. And PMOS, first PMOS we have Z power y. Initiation, like this power, consider only this power. You have output z and power, and for this I mean this PMOS is connected. I'll clear it out. Here we are considering first PMOS represented as z power and y. This PMOS connected with z power and y. Okay, now let us consider with next PMOS. It is connected with yzx. So how it is connected? Next PMOS, so it is connected in this way, like x connected, z connected, and y connected. Okay, and NMOS out and ground and x, like where is one NMOS? This is okay. I will take another color, and this NMOS is taken into ground, x, and out, and another NMOS. Let me take another color. This NMOS is considered for this thing, and you have output y and ground. Okay, so just initiations. Once you declare the connections in this way, once you declare the connections in entire circuit, you can end the module. That is how switch level modeling can be done. Just a representation of the logic circuits, and hence these are all switching sitting inside the core processor, and these are the RAMs and SDRAM, some block RAMs, SRAMs, and flash memory. So yeah, this is the architecture of FPGA, you can see, and that's our class today. So if you have any questions, just let me know. I'll be happy to answer, and connect with me if you have any difficulties in attending or learning these things. I'll sort it out. So thank you for attending again. See you in the next class.